Hello, everyone. Again, this is Allie from the CAE team. I'm just filling in for Josh since he couldn't be here today. Thank you for being with us. We're now going to have Dr. Massimiliano Albanese from George Mason University presenting on a metrics-driven approach to prioritizing vulnerability mitigation. Thank you, and you can go ahead.
Thank you for the introduction. So a little bit about myself. I'm an associate professor and as of last month, the associate chair for research in the Department of Information Sciences and Technology at George Mason University. I'm also serving as the associate director for the Center for Secure Information System. And I'm also a consultant for the MITRE Corporation that I'll mention in this presentation. I have a PhD in computer science and engineering from the University of Naples, Federico II in Italy. My research interests are in the broad area of network security with focus on graph-based modeling, metrics, and network hardening, among others. Brief outline of this talk. I'll provide an overview of the issue that we are trying to address and along with some motivations. I'll give an overview of our contributions, and then I'll discuss the vulnerability metrics that are the core of this work. And one application of those metrics being a system for scoring common weaknesses as defined by MITRE. And I'll go over the system that we have actually built and made available to the community, to the broader research community. And I will conclude by giving some indication about what are our future directions in terms of research. So what is the problem? The problem is that when you consider a large network, large distributed systems, typically there are many hundreds, possibly thousands of unpatched vulnerabilities and weaknesses that are exposed to potential malicious actors. Of course, everybody wants to do vulnerability remediation, mitigation, but given limited resources, organizations have to come up with ways of prioritizing which vulnerabilities or which weaknesses needs to be addressed first. Several organizations, including NIST and MITRE, have established some frameworks, some scoring systems to help in this process. All of these are critical tools to help security administrators make informed decisions about vulnerability remediations. However, as I will show through this presentation, approaches that exist currently have some limitations. Some of the scoring systems are too rigid or too coarse-grained to provide useful information. In terms of current solution that exists for the community, probably most of you know that NVD has a vulnerability database maintained by NIST, which assigns to each CVE a vulnerability score called CVSS, Common Vulnerability Score System. Also, MITRE every year publishes a ranking of the top 25 common weakness enumeration entries and always publishes the top 10 web application security risks. So all of these are mechanisms based on metrics to score and rank weaknesses or vulnerabilities. The problem with all these solutions is that they all rely on some predefined notion of risk that cannot be adapted to different situations. They use predefined and fixed equations to compute numerical scores that cannot be changed. And in other words, they do not provide users with the flexibility to fine-tune these equations and to consider new variables, new data in the process of scoring vulnerabilities. And last but not least, all these scores are updated not very frequently. So I mentioned MITRE, the ranking that they provide, it's published once a year. In terms of tools that are available to the community, what we have right now, it's a set of disconnected tools. We have vulnerability scanning tools that will help organizations figure out what vulnerabilities exist in their systems. We have vulnerability scoring frameworks like the one that I've already mentioned by NIST, MITRE, and others. We have attack graphs that can help model the relationships between different vulnerabilities. And also we have network hardening tools, which enables organizations to identify conditions that can disable or enable the ability for users or malicious users to exploit vulnerability paths. And since I mentioned MITRE, this is the most recent CWE top 25. As you can see, there are, only 17 in this screenshot, but MITRE basically publishes this every year. Each line on this table is a weakness, which is a more abstract concept than vulnerability. Each weakness may include several hundreds or even thousands sometimes of different vulnerabilities that fit into that description. And each of these classes of vulnerabilities is assigned a score, numerical score, and a rank. And this table also shows how the rank has changed compared to the previous year. Some entries have gone up in this ranking, some have gone down, most of them have remained pretty much stable. Now, one issue here is when publishing this ranking once a year is that in the cybersecurity landscape, things can change pretty quickly. And vulnerabilities are discovered pretty much every day. And if you look at this snapshot from the National Vulnerability Database, I mean, this snapshot was taken back in May when we published this paper. But essentially what you see is that at any point in time, there is a significant number of vulnerabilities that have been recently submitted, others that are waiting for analysis, and others that are in the process of being analyzed and assigned a score. So every day, there's new data coming into this database. And what MITRE does in computing those CWE scores, it uses CVE data from the previous 2 calendar years to have aggregate scores for the individual CWEs. Is this sufficient? No, because as I'm explaining, data changes constantly. So how we try to address this? We try to address this by creating a more flexible vulnerability scoring framework that, first of all, allows users to generate custom rankings, giving them the ability to fine-tune several parameters that are used in the calculation of vulnerability and weakness scores. This work builds on our previous work on vulnerability metrics, and similarly to what MITRE has done, aggregates vulnerability level metrics to compute weakness level scores. One of the major differences with what MITRE does is that we publish monthly rankings instead of yearly rankings. Not only that, but we also allow users to generate monthly, weekly, or even daily rankings on demand based on their own needs and based on their own configuration parameters. Now, next, I'm going to go over the 2 key metrics that are part of this framework. One is the exploitation likelihood, and the other one is the exposure factor. The exploitation likelihood of a vulnerability is essentially the probability that a vulnerability will be exploited if all the preconditions are met. What we've tried to do in this line of work, we have tried to figure out what factors, what variables can influence an attacker's decision to use to exploit one vulnerability versus another. Now, of course, a big factor is what CVSS defines as the exploitability score, which is one of the 2 pieces that go into the overall CVSS score that is published by NVD. And in turn, the exploitability score takes into account things, how difficult a vulnerability is to exploit and things like that. But we concluded that that is not the only parameter or only variable that influences an attacker's decision to use a vulnerability. One other could be the amount of time that vulnerability has been known. And the rationale for this is that the longer a vulnerability has been around, the more likely is that the hacker community has developed exploit tools to be able to exploit that particular vulnerability. So these are things that influence or increase the chances that a vulnerability will be exploited. But there may be also variables that decrease the likelihood that a vulnerability will be exploited. And in our analysis, we found that one of those could be the number of known IDS rules associated with that particular vulnerability. The rationale for this is that when an attacker has many different vulnerabilities available to attack the same system, he may choose to use vulnerabilities that are less detectable because there are less intrusion detection rules associated with them. So essentially, an attacker who wants to be stealthy may want to pick vulnerabilities that are not very easy, whose exploit is not very easy to detect. Now, the other metric is what we call the exposure factor, which is a term borrowed from traditional risk analysis. So essentially, the exposure factor of vulnerability represents the relative damage that will be caused to an asset by the exploitation of that vulnerability. Now, even in this case, there are several variables that can contribute to the exposure factor. The primary variable that contributes to the exposure factor is the CVSS impact score, which measures the impact of an exploit on the integrity, confidentiality, and availability. Again, like we did with the likelihood, we try to identify other factors, other variables that could influence the exposure factor. And we identified the set of deployed intrusion detection rules as one variable that could mitigate the effect of an exploit. So I'm saying deployed intrusion detection rules. What that means is that when you deploy an IDS, the IDS comes with a set of predefined rules, and you can decide which one you want to use and which one you don't want to use. The ones that are actually used to actively analyze and monitor traffic are the ones who can identify potential intrusions. And if you're able to identify potential intrusions or exploits as soon as they happen, that enables you to respond timely to those intrusions. And by responding timely to those intrusions, you mitigate the effect of that exploit. You may mitigate the impact of that exploit. And that's why we consider that as a variable that contributes to decrease the exposure factor of a vulnerability. Now, the question is, and before I go to the generalization of these rules, I have a little slide just to recap this use of intrusion detection rules as part of this ranking process. And again, I've mentioned known IDS rules and deployed IDS rules. And the difference is that known IDS rules are the ones that are known to the community. So in that case, also to the attackers. And deployed IDS rules are the ones that are actually used. Known IDS rules contribute to reduce the likelihood. Deployed IDS rules contribute to decrease the exposure factor. Now, how this vulnerability level metrics can be used to compute scores for CWEs, which are a higher level concept, and with each CWE being an aggregate of multiple vulnerabilities. So these formulas on this line is essentially the process that MITRE uses to compute a CWE score. And the CWE score of a CWE is essentially the product, is the normalized product of the frequency or number of CWE, the relative frequency of a CWE and the average severity of that CWE. Now, the frequency of a CWE is computed as the normalized frequency or normalized cardinality of the number of the set of vulnerabilities associated with each CWE. And the average severity is simply calculated as a normalized version of the average severity of vulnerabilities in that CWE category. So these are aggregate functions. Now, what we have done to, in a sense, reproduce this process by using the more generic vulnerability level metrics that I've just defined is to come out with our own equivalence score. So we compute this equivalence score as the product as the average likelihood of the vulnerabilities in a CWE category and the average exposure factor of those same vulnerabilities. And then we define the score for a CWE as the product of the number of CWEs in a number of vulnerabilities in that category and the average and the severity score that I've just defined. Now, this may seem a little bit complicated, but if I show the formula side by side, it will be much more clear. So this is how MITRE compute a score for a CWE. The relative normalized frequency times the average severity, normalized to be between 0 and 100, and we computed as the number of vulnerabilities in that CWE category times our own version of the severity score. As you can see, we do not normalize this score because for the purpose of ranking, it doesn't really matter. And at the same time, it will save us some computations. Now, combining all these formulas together, we get to this big formula. Now, the next issue here is we started from looking at MITRE, which only uses essentially CVSS scores to compute the aggregate score. And those are the exploitability, CVSS exploitability, and CVSS impact. And we argued that those are not the only factors that should be considered, and we explored other variables that should be considered in this process. In a similar way, somebody could say, okay, what about you're forgetting any variables that still may have a role in this? So in order to do that, we generalize this process to allow users and others to basically expand the set of variables to be considered in this process. But before I show you the generalized formula, I want just to recap what is the semantics of all of this and what is the logic behind what we're doing. So the central point here is that vulnerability exists in systems and they can be exploited. The probability that a vulnerability can be exploited or will be exploited is what we call the likelihood. Once a vulnerability is exploited, there will be consequences for the system and some damage will be inflicted to the system proportionally to the exposure factor. Now, if we're looking at the likelihood, there are several variables that can influence the likelihood. Those include intrinsic features of the vulnerability, so how intrinsically complex to exploit a vulnerability is, or external variables like the availability of intrusion detection rules to detect the exploitation of a vulnerability. Similarly, when we're looking at the exposure factor, there are intrinsic features of the vulnerability that determine the exposure factor, such as the ability of that exploit to impact the confidentiality of the information or the integrity or the availability. But as we saw, there may be other external variables like the availability of deployed IDS rules that could mitigate that exposure. So this is the logic. Now, if we expand the set of variables that can be used in this process, the question becomes, how do I know which variables should I use depending on the situation? The reality is that depending on the attacker that you're facing, you would use a different set of vulnerabilities in computing the likelihood. And the reasoning is a more sophisticated attacker will have more information at their disposal, and therefore they will make their decision based on this this broader set of information. A more naive attacker may make decisions based on fewer pieces of information. So we can use that logic to decide how complex or how more or less or complex we can make the definition of the likelihood. With that, let me jump to the generalized formulas for the likelihood and the exposure factor. So as you can see, this is the formula for the likelihood, which has a similar structure to what we saw before, but in the previous case, we had instantiated this with only three variables. Now I'm generically saying that there is a set of variables, XL with the arrow up, of variables that contribute to increase the likelihood of a vulnerability. There is another set of variable, XL with the down arrow, which contributes to decrease the likelihood of a vulnerability. And similarly, there is a set of variables that contribute to increase the exposure factor and a set of variables that contribute to decrease the exposure factor. The variables increasing the likelihood are multiplied at the numerator, and the other ones are at the denominator. Now, each of this variable contributes to the overall likelihood as a multiplicative factor between 0 and 1. So this thing in parentheses always evaluate to a number between 0 and 1. With zero being zero likelihood, meaning the vulnerability cannot be exploited, and 1 being the vulnerability will definitely be exploited. Now, the way this is formulated not only normalizes each factor between 0 and 1, but also allows you to consider diminishing returns as the value of the variable increases. So this is an exponential formulation, in fact, going asymptotically to 1. Now, if you look at the exponent of this, there are two things. One is alpha x is just a constant that can be tuned by the users to give different relative weights to the different variables, but also to control how quickly the contribution of this variable go to the asymptotic value of 1. And the other important element is a function of the variable. Now, the reason why we do this is because to make this model as general as possible, we have no restrictions of what a variable could be. Any piece of information that I can attach to an individual vulnerability, whether it's a number, whether it's a set of objects, like a set of intrusion detection rules, or a set of Nessus plugins that are specific to that vulnerability, I want to be as general as possible. So fx is simply a variable, a function that transforms complex variables, variables with complex values, to scalar values that we can plug into this formula. So one example could be if we're dealing with a variable that represents the set of intrusion detection rules associated with a vulnerability, this function could simply be the cardinality of that set of vulnerability. Now, if there is any question at this point, I'm happy to take questions before we jump and move on. So feel free to interrupt anytime. So in conclusion, this model allows us to plug in any information that a user or administrator believes is important to define the likelihood or the exposure of each individual vulnerability. Now, on the practical side, this research has led us to build an actual system that we've made available to the public through a web interface. We call this system the Mason Vulnerability Scoring Framework. And this framework is composed of a backend, which includes 3 main modules, and a front end, which is a graphical user interface realized through a web application. So now I'm going to go through these different modules and discuss what exactly they do. The 3 modules in the backend are a data ingestion module, a metric computation module, and the ranking module. Currently, this system ingests different types of information, vulnerability information from the National Vulnerability Database, as well as intrusion detection rules from public repositories or local rule files that you can find, for example, in your IDS installation. But this framework can be easily, this module can be easily extended to ingest additional data as long as we can map that data to a specific CVE ID. This module periodically, using, of course, a cron job, periodically fetches data from NVD and updates the internal database. And as well, periodically pulls new IDS rules from available public repositories. Internally, the data is normalized and put in an internal database. Clarification related to IDS rules, if you look at IDS rule files, they may contain a lot of rules. Not all of them are necessarily associated with a specific CVE ID. So we're only interested to those who are specifically associated with the CVE. The second module is the metric computation module. This module essentially implements a suite of algorithms that compute all the metrics that I've mentioned so far. and it computes both vulnerability level metrics, like the likelihood and the exposure factor, and weakness level metrics, including CW scores. So this particular module is triggered by different use cases. Every time, for example, new data is ingested, likelihood and exposure factor of individual vulnerabilities are either computed for new vulnerabilities or updated for vulnerabilities that were known before, but for which new data became available. And it is also triggered by the ranking module that I will discuss in the next slide. So every time a user requests a custom ranking, or every time we compute an official monthly ranking, this module is invoked to compute the vulnerability level metrics, and then using those, the weakness level metrics. And then finally, the third module is the ranking module, and that produces a ranked list of CWEs. So there are two ways of running this module. One is periodically. So there is a automated process that on the first day of every month computes new rankings based on the data up to the last day of the previous month. And this is published on the website. This process is very efficient because all the underlying vulnerability level data and vulnerability level metrics have already been computed as new data was fetched from the source. Or this can be run on demand, so where users can request specific rankings specifying all the parameters that they want. This process is a little bit more intensive computationally because we cannot predict what rankings the user will request and what parameters they will specify for each of the vulnerability metrics. Now, in terms of the user interface, this system is available as a web application at the URL that I've provided on this line. Anybody can go and request an account. The account needs to be moderated. It needs to be approved. We only do that to prevent spam and requests coming from strange sources. When you log into this system, the landing page will show you the most recent ranking. So today is October something, so it will show the ranking as of the last month, as of September. And then on November 1st, it will calculate the new ranking based on data up to October 31st. Similarly to what I've shown you for MITRE, this shows how the rank has changed compared not to last year, but compared to the previous months. The other interesting thing we do is, as I say, we publish these rankings every month as opposed to every year. So what we can do over the course of a year, we can observe and we can actually highlight trends in the evolution of this score. So we can see when a specific CWE over time starts to become more or less severe. So this provides a visual to the user, and the user doesn't have to wait for a whole year before understanding what the trend is with specific CWEs. Now, so this is a similar view, and the difference between what we call the historical rankings, these are rankings that are computed the first day of every month and are frozen. The interesting thing is that because MVD is updated frequently, even data that was already in MVD, it may be later on updated, revised because of new information becoming available. In that case, our historical monthly rankings that have been pre-computed earlier will not be modified. It will just provide a record of what the ranking looked like at that point in time. But in our dynamic view, we will keep updating the rankings based on any new data that becomes available. So this provides a dynamic view. And in this view, the user can also tune the parameters. And then one last level of customization is allowing the user to provide fully custom rankings where not only the user can specify the parameters for the different vulnerability metrics, but you can also specify the time frame of the data to be considered for the ranking. The views and rankings that I've shown before, they are all based on a 24-month period preceding the date of the ranking. And this was done to be consistent with MITRE's approach, where MITRE uses 2 years worth of data for the ranking. In this fully custom ranking, the user can choose and can slice the data in whatever way they prefer. They can compute rankings based on 12 months worth of data, 5 months worth of data, or whatever they prefer. Now, I want to go back for a second to the idea of CVSS scores and why they are limited. Now, what I've shown here in the previous slide is how you can rank weaknesses. And the question is, can we do the same for vulnerabilities so that at the vulnerability level, I can identify which vulnerabilities are more critical than others? The problem with CVSS scores is that they are two cores. Now, if you look at the definition of the CVSS exploitability score, is defined as this product, is the product of access complexity, authentication, and access vector, where each of these variables can assume only one of 3 discrete values. So if you do the math, this gives you only 27 possible values of the exploitability score. And if you do a similar reasoning for the impact score, where the formula is this, and essentially it's still the product of 3 factors, but this time the values are the same for each of the 3 variables, which means that is even less, because this is the number of combinations with repetitions, which is only 10 in this case. So again, when you combine these 2 scores to compute a aggregate severity score for the vulnerability, essentially you have at most 270 possible values of the severity score, but we have hundreds of thousands of different vulnerabilities in NVD. So clearly, these scores are not sufficient to properly discriminate between so many variables. So that's one of the reasons that justify why we need to consider more variables when computing and evaluating a score for a vulnerability. And this little illustration here should further clarify this problem. So if we try to rank vulnerabilities the same way we have done with weaknesses, using just CVSS scores, but the exploitability score and the impact score, we would end up with a situation where there are 167, if you look at the table in the middle, 167 different vulnerabilities with exactly the same score. And the reason is because of the limited number of options that you have for the values that contribute to define the CVSS scores. So if we decided, even worse, if we decided to ignore, for example, the role of the impact score, and we only rank vulnerabilities based on their exploitability score, the situation would be even worse, because we would have 9,000 plus vulnerabilities with exactly the same score, which would make impossible to identify which one is more severe, which one needs to be addressed first, which one are the top 25. We don't have the top 25 because we have too many with exactly the same rank. Now, if we do the opposite and we move to the right of this figure, where instead of eliminating variables, we add more variables, then what happens is you can see that now the number of ties between vulnerabilities becomes much, much smaller. In this case, by adding this additional variable, we only have 8 different vulnerabilities with exactly the same score. Again, this is an additional way of justifying, motivating why in scoring vulnerabilities, we have to go beyond CVSS and consider other sources of information, other variables that can influence either the likelihood of exploiting a vulnerability and the potential consequences of that vulnerability being exploited. And I'm going to wrap up so we'll have time for QA. So essentially, this framework that we have created, it's intended to be a flexible framework for scoring vulnerabilities and weaknesses. And the idea is that any system that scores weaknesses and vulnerabilities should be responsive to the fact that in this landscape, information about vulnerability changes very frequently. And different users may have different needs, different priorities. In terms of future work, what we want to do is we want to build a comprehensive framework that can integrate different capabilities related to vulnerability analysis. So we want to move the focus from vulnerability-centric, which has been the focus so far, to organization-centric. So far, all of these rankings are universal rankings that apply irrespective of what is your specific architecture, what are the specific vulnerabilities that exist in your system, and so on. So we would like to integrate this process with things like vulnerability scanning, attack graph generation, so that the rankings and scores that we produce are specific for an organization rather than being generic. Also, the fact that things change over time, and the fact that we can see trends in the past gave us the idea that probably we should start thinking about predictive analytics to try to anticipate some of these trends in how severity of vulnerabilities evolves over time. And essentially, the long-term vision for this is to create a vulnerability scoring as a service system where these capabilities can be offered as a cloud service for integration in third-party applications. As I said before, and just a reminder, this is available. So if you like to see how it works and have an account, of course, this is all experimental. Still work in progress, but the application is up and running. You can go here. You can either type the URL or scan this QR code, and that will take you straight to the login page. And then at the bottom, you can click here to say, request an account. One last thing I want to mention, we have had ongoing discussion with MITRE's team who works on CWE. We have had several exchanges. We're initiating a collaboration. We have had several discussions, and they also mentioned this work on their own website if you follow this link. And interestingly enough, after we came out with this idea of visualizing trends in the evolution of CWE scores, in the most recent update of their CWE Top 25, they've included graphics like this one, where they're showing the trends in CWEs over the years. So this is a similar idea to what we had implemented, but it's done year by year rather than month by month, because they only have rankings on a yearly basis. These are the publications related to this topic that we have so far. So the first piece of this work, appeared in SecRep 2021, and we're working on an extended version of this work that will appear soon in Elsevier Computer and Security. And then the framework itself, and that I've described in, let's say, the second part of the talk, this has been presented this past July, again in SecRep 2022, and this particular paper won the Best Paper Award at the conference. And finally, I want to acknowledge the organizations that have contributed over time to this research. This work was initiated as part of a joint project with Palo Alto Research Center through a grant from DARPA. It has also been, it was also funded in part by the National Science Foundation and by the Commonwealth Cyber Initiative. And this is just a list of students who have been involved at different stages through this project. Questions?
If anyone has any questions for Dr. Albanese, you can go ahead and put in the chat, or you can unmute yourself. The first question is, did you consider MITRE's exploit prediction scoring system?
Prediction system, not yet, not yet. This is on our to-do list. Thank you for the question. You can also unmute yourself and ask the question live if you like.
Hello, thanks so much for the talk. So this is Mustafa Abdallah. So yeah, I have a question related to the attack graph because in my work, like I tried to model the systems in which there are different vulnerabilities. So do you consider like aggregate score or like paths or attacks that consider multiple vulnerabilities, not just a single vulnerability?
Sorry, can you repeat the
Yes, I
question?
will. Yes, for example, if in interdependent system where there are
Mhm.
some components, you take control of one component via vulnerability X, you can use that to target another
Right,
component,
right,
another
right.
asset, even a
Mhm.
vulnerability Y. Is
Right.
there
So
like, does your system or does your score support such aggregation? Because, like for example, in my previous works, I use like simple CVE multiplication of the CVSS scores. So, like, do you have any insight on that?
right. Okay. So this is a good question. Actually, the project with DARPA, I mean the DARPA project with Palo Alto Research Center involved modeling systems through a complex graph that included three components, one of which was the attack graph and one of which was the dependency graph. Okay. So if you look at an attack graph, basically shows you multi-step attack paths where an attacker exploits a vulnerability and then creates some conditions that enable him to exploit another vulnerability. Okay. So the edges between those vulnerability nodes in the attack graph that we used were labeled with probabilities. Okay. So once the attacker exploits a vulnerability, it opens up multiple options in terms of what other vulnerabilities can an attacker exploit next. So what we did, and I've not included that in this presentation, but what we did, we used the likelihood score to essentially compute as a basis for computing the probabilities of those edges. Now, the likelihood as we computed is it can be interpreted as a conditional probability, which means it's the probability that you will exploit a vulnerability if you have all the preconditions. And preconditions mean you have access to the vulnerability, you have all the credentials, the tools, whatever you need to go and exploit. Now, of course, if there is a vulnerability that is one hop away from the entry point, so that the attacker first needs to exploit one vulnerability, then needs to exploit the second one, what we define is an adjusted likelihood for the second vulnerability, which takes into account the path that leads to it. So we cannot just use the absolute, I mean, that conditional probability, because we need to consider the probability also of realizing the condition that will allow that vulnerability to be exploited.
I see. That's great. Thank you so much.
So in the context of attack graphs, those likelihoods that we compute for individual vulnerabilities can be used as a basis for computing the probability of the edges and the adjusted absolute probabilities of reaching, you can call it probability of reaching in each individual vulnerability that is inside that attack graph.
That's great. So I will, sorry, just a follow up. Just a general question for validating the scores itself. So like, is there a way like for like more practical way to validate these estimated scores, like either by the CVE or like your nice like way to estimate the probability of exploit scores? Because I mean, like how to validate that these scores are represented, can represent actually in reality the real likelihood of success. So also
Right.
this is something I got like a lot of feedback regarding my work doing.
Yeah, that's a very good question, and that's something we face all the time. So what we did, I think, with the first paper, since we had come out with our own vulnerability scores, what we did was to basically compare our ranking of CWE, where again, the score assigned to a CWE aggregates vulnerability level scores for all the CVEs that are in that CWE category. So to do that, we we use our vulnerability level metrics to compute the CW scores, and then we compared our ranking of CWs against MITRE's ranking. Because we said MITRE's ranking is well recognized, it's been vetted, and if we tune our system, okay, so our system is a lot of tunable parameters. MITRE's system is a fixed set of formulas, and that's it. So basically, we tuned our system to make the operational context as close as possible to what MITRE describes, and then we ran it, and then we compared the two rankings, and we got a very high correlation. I think it was between 80 and 90%. So our ranking correlated 80, 90% with MITRE's one. So that gave us confidence that we were on the right track. But then, of course, when you start adding more and more variables you don't have a ground truth to compare against, because nobody else has the idea of, for example, including IDS rules as a factor in the decision process. Okay. And it's true, it's not true, depends and that's why we added these additional dimensions of saying, depending on the attack model and what attacker you are expecting to face, the set of variables that you need to use is different. So if you don't think that the type of attackers you're facing is going to look at IDS rules and is going to be discouraged by the fact that certain vulnerabilities as 5 IDS rules, so that if they even try to exploit it, it will be detected immediately. If your type of attackers will not be discouraged by this, then you should not consider the variable, because it will not give you realistic results for your particular attack scenario. So in our more general model, where I came out with those more generic formulas, the decision of what variables to consider for each of those 4 groups has to do with your expected attack model.
Okay, thank you so much for this one. Thanks.
Sure.
Any other questions?
Somebody, what is this? Patriot Web? Yeah, there's something in the chat, but I don't know what.
Yeah, I'm not sure what Patriot Web means. If
Patriot Web is our amazing is our system for several, internal systems. I don't know why somebody sounds familiar, but.
And did you have a slide with your contact information or no?
Not really, but I can post my.
Only if you want to. I was just making sure we didn't miss anything.
Sure, I can. Yeah, I forgot to do that.
Then if no one else had any questions, thank you very much, Dr. Albanese, for joining us. Dr. Albanese, thank you.
The opportunity.
Of course.
Thank you.
Dr. Albanese has put his email in the chat if anyone wanted to reach out to him. In regards to the recording for today, you can email caepmo@nsa.gov. That's caepmo@nsa.gov. I also put that in the chat earlier. And we could try to send you the recording once we get that processed, or send any other questions that you have. Thank you again for joining us. We really appreciate it, and have a great rest of your day, everyone.
You too. Thanks.
Okay, thank you so much. Bye.